All right. So now I think we are recording. So I guess I just wanted to send a message whoever is watching it remotely on YouTube or later asynchronously. We're just looking at the midterm. So whoever did not get a chance to see their midterm, or you can tell your friends too, then you is holding on to them. So just make an appointment with him or go to his office hours. If you feel that you were taken off too many points in unjust way and you want to submit a regrade request, then also please post it on Piazza to the instructors, and we will collect them. I guess we should make some deadline to it, right? Like maybe like in 2 weeks time at most. I might send some. You want to send some official instruction? Oh, I think we said 1st December, right?
Yeah, maybe December.
Let's do like a 1st December, so then we collect it, and then we see. Then we look at all the requests together and make sure that everybody's treated fairly, okay? Sounds good. Okay. Any further questions regarding the midterm? Okay, so thanks. We can go. Oh yeah, other thing, I posted the project number 5. Have you noticed? That's the plucking the string. This is a sequence of springs which forms a string, and then watching how it oscillates by taking the exponential of the matrix as we discussed on Monday. And that project won't be due until Wednesday next week. It's because I was thinking if I could even give you more. There won't be any homework next week because there is a Thanksgiving week. Then it won't even be class on Wednesday. I got some instructions, some official instructions which seem to be open to interpretation. But anyway, we did a vote. We took a vote earlier, and vast majority of things was interested in canceling the lecture as opposed to holding it. So I guess to facilitate Thanksgiving travel and so on. So there won't be any lecture on Wednesday. Okay? And there won't be any homework either. Then we need to finish. Yeah, that's gonna be good. But your project number 5 will be due on Wednesday, I guess midnight as usual. All right? Okay, so let's do symmetric matrices today. So I talked a little bit about anti-symmetric matrices or skew-symmetric matrices, right, on Monday, because I thought it was cool. Because the skew-symmetric matrices, they are generators of rotations, and by generators, they generated via the exponential or via solving a system of linear differential equations. And today we are going to look at, let me make this bigger. Today we are going to look at even more important class of matrices, which are symmetric matrices. So you already know what a symmetric matrix is, right? It's a matrix such that its transposition is the same matrix, which immediately implies the matrix must be square, right? If the matrix is rectangular, we don't talk about symmetry of the matrix. Because if you transpose it, you still need to keep the same dimension, so you can even think about that being the same or not. What happened to the foot? And it turns out that symmetric matrices have some beautiful properties in terms of eigenvalues and eigenvectors, and that's essentially the key to a single value decomposition. So if I should motivate it somehow, we have seen that there are all sorts of problems if we are trying to do eigenanalysis of general matrices. So first of all, even before I even start thinking about eigenanalysis, the matrices have to be square, right? When we talk about eigenvalues, eigenvectors, this type of relationship, we are only talking about it for square matrices, right? Because this AV has to have the same dimension as V, so A must be square. So the first question would be how to generalize it to the rectangular matrices, right? And even if we talk about square matrices, there is still a problem because, as we have seen, not all matrices are diagonalizable, right? There's the problem that there will always be n, maybe complex eigenvalues, but there might not be a full set of eigenvectors for the non-diagonalizable matrices, the simplest one being this, right? This matrix simply does not have 2 linearly independent eigenvectors, so there is no way to diagonalize it. So the way to get around all these problems and generalize the idea of eigendecomposition to rectangular matrices and to defective matrices like this, that's SVD, single value decomposition. And it turns out that the key thing to SVD will essentially involve looking at ATA, or almost equivalently AAT, Okay, so if you have a matrix A, which is a problem, either it's a defective or it's a rectangular matrix, what we will do, we will form ATA or AAT. That doesn't matter, in both cases it's the same idea. And this is always a square and symmetric matrix, okay? And on symmetric matrix, and that's why we are going to talk about symmetric matrices today, because they have some special properties that make eigenanalysis easier. Okay, so let's start talking about symmetric matrices. So this is basically just a quick summary of what I was saying. So there will always be n eigenvalues if you have a square matrix, right? Which some problems are they might be complex and they may or may not be distinct. You might have just repeated eigenvalues, right? Like eigenvalue 0 or 1 or whatever can be there multiple times, like multiple. What's it called? It appears multiple times as the root of the polynomial. That's what I was writing, like x minus 1 to 100. It will be 100 times the same eigenvalue. So the point of symmetric matrices is that all these problems essentially go away. So symmetric matrix, as I said, it must be square, and ATA is 8, that's what symmetric means. And if you have a symmetric matrix, then I claim, and I will prove in a little bit, that all the eigenvalues are actually real. So all the problems with complex eigenvalues go away. If eigenvalues are real, that means that the eigenvectors must be real as well, right? The only reason why eigenvectors would be complex, the complex numbers could only enter through the eigenvalues, right? Because how do we solve for eigenvectors? We look for the null space of a minus lambda I, right? Well, if lambda is real, then a minus lambda I is real, so there's no way how complex numbers could appear there, right? Just by doing linear algebra. So automatically, eigenvectors will also be real, okay? And it gets even better. So this is just like this is like good news and more good news about symmetric matrices. So in every case, a symmetric matrix has the full complement of eigenvectors, okay? So there can be any defective matrices, and even better, these eigenvectors can be made mutually orthogonal, okay? We had a weaker statement before. We had a weaker statement was saying that if we have full set of eigenvalues such that all of them are distinct, we can get a linearly independent basis of eigenvectors, okay? That was the eigenvalue decomposition. That was the requirement for the matrix to be diagonalizable. So in the symmetric case, not only it always works, I don't have to assume that the eigenvalues are distinct, but even better, the eigenvectors are mutually orthogonal. So that means that if I form the matrix of eigenvectors, so if Q is the matrix which every column of Q like this, every column of Q is an eigenvector, then this matrix is actually going to be orthonormal. So I guess this is what I'm going to get to. So I will prove some of these properties, not exactly all of it, because I don't have time to do all the proofs, but I will at least show you the most important ones. So I guess these are the reasons why symmetric matrices are so important, because the eigenanalysis has all these beautiful guarantees, which in turn is the reason what makes SVD work. Okay, so let's first take a look why the eigenvalues of a symmetric matrix are real. Okay, it's a little bit technical proof, but it's not so difficult. So I'll just discuss it. So let's take a look at it. So let's assume that V is an eigenvector of A with eigenvalue lambda. And we don't know yet if it's real or not real. So let's assume in general it's complex. And what I will try to prove here in this proof is that, in fact, that lambda must be real. Okay. Okay, so let's assume it's real numbers are, of course, a subset of complex numbers, right? So that's fine. So let's just assume it's complex now. And let's take the complex conjugate of it. Okay. And V complex conjugate, that's the complex conjugate of the eigenvector V. Okay. Now we assume that A is real and symmetric. Okay. So taking the complex conjugate of A does nothing, and taking the transposition also does nothing. Okay, that's because so one is from the symmetry, the other one is from the assumption that A is real. That's from my assumptions. Okay, and here I can start playing some tricks. So here this is the eigenvalues formula, right? This is saying that V is an eigenvector with a lambda as the corresponding eigenvalue, and this. Well, yeah, this is trivial. So if we conjugate everything, that conjugating A does not change anything. Okay. And what I can also do is transpose this entire thing. Okay. So I take A V conjugate, the whole thing transpose, but it will be V conjugate transpose A transpose, but A transpose is just A. Okay, so that's what I have here. Here I have just transposed the V conjugate. And the lambda conjugate, that's just a scalar multiplication. It's a complex scalar multiplication, but it's still commutative, so it doesn't even matter if I write it on the left or on the right. Okay. So that's easy, and let's do the following trick. So this first equation, we take this, and we dot product it with V conjugate. Okay. So if we do that, we will get here. So if we do V conjugate transpose AV, that's what's here, and this is V conjugate transpose V. Okay, that's what we have on the right hand side. So if this was equal, of course, after the dot product, it's equivalent, right? It goes both ways. So that's one way we can look at this, but we can also take this formula and dot product it from the right with V. Okay. So that means we take this V conjugate transpose A and do times V, and V conjugate transpose lambda and times V. So this gives us this formula. Okay. So notice, the important thing to notice is that here is lambda conjugate versus here was lambda not conjugate. And what we have here, let's take a look what we got. So here we have this and this. So the first thing you want to notice is that on the left hand side, this term is the same. V conjugate transpose AV, V conjugate transpose AV. Okay, well, that means that the right hand sides must be the same too, right? So that means, if I should write it, that means that lambda V conjugate transpose V must be equal to lambda conjugate V conjugate transpose V. Okay. And we are almost there. The only thing we need to realize now, what is the V conjugate transpose V? Okay, let's take a look at it. What is it? V conjugate transpose V. So if it's an n-dimensional vector, then I can just write it by coordinates, right? So it's from 1 to n, Vi conjugate Vi. And that's just the sum of the squared norms, right, of the complex numbers. So Vi's here, Vi's are complex numbers. I am summing their squares. And so these are, of course, real numbers, right? If I do a complex conjugate times itself, I'm getting a real number, right? Or square norm, that's definitely a real number. And because V was an eigenvector, it could not be a zero vector. Okay, that's what we forbid. I spent a lot of time explaining why do we not allow zero eigenvectors. So V is not zero. So that means that this is strictly greater than 0. Well, that's great, because then this means this is just a real number which is greater than 0. So what I can do, I can divide by it. And if I divide by it, I will have to conclude that lambda equals lambda conjugate, right? And if a complex number equals its conjugate, that means that the complex part has to be 0. That's the only way this can be true, okay? And that proves that the eigenvalue indeed must be real. Okay, and it's all hinging on the symmetry of A. The key thing was that when we transposed it, we just got the A back. If it was not symmetric, you would not get this result. Yeah, so this is a proof, a simple proof. which I don't think it gives you too much of an intuition. It's more like a technical type of thing that you just lay down the facts. It's like sort of like I guess like a lawyer or advocate, like constructing a line of argumentation that leads to the result. But some important facts. So it's good to realize that the proof is not complicated. Okay. Well, I think, as I already said, it's easy to realize that if we have all eigenvalues real, that the eigenvectors certainly also be real, right? I think I was talking about a little bit. Well, that follows from the fact that this matrix is real, and the eigenvectors are the vectors of the null space, that are the null space vectors in the null space of this matrix. So if it's a real matrix, then of course the null space must be real too, right? So there is no way we would have to deal with complex eigenvectors in this case. Okay, so let's take a look now on the other part of the statement. I guess the second good news I had about symmetric matrices. I guess let's look at the simpler case. It's or like a weaker statement, and there is a stronger version of this statement which is still true, but I will not be proving it here, even though it's still true. But let's look at this one because that's easier to deal with. So the statement goes like this. So if you have a symmetric matrix and we have eigenvectors corresponding to different eigenvalues, then we claim that they must be orthogonal. Okay, so that's a stronger. That's similar to what we had before, right? Before we had for arbitrary matrix, which didn't have to be symmetric. If we had eigenvectors corresponding to two different eigenvalues, then what we proved before was what? What we already know from what we discussed before. If we take two eigenvectors and each of them has a different eigenvalue, what we can conclude about the eigenvectors. I remember I was proving it. It was like this ugly proof with lots of lambdas and c's. I think I said it also a couple minutes ago. We already know that they are linearly independent. Okay, but this is stronger, right? If two vectors are orthogonal, they must automatically be linearly independent, right? But not all two linearly independent vectors must be orthogonal, right? Orthogonal means this. Linearly independent could be this, right? Just got too lazy that I'm not even bothering drawing it. Okay, so let's take a look how to prove this. So let's assume that v1 is one eigenvector corresponding to eigenvalue lambda 1, and v2 would be another one with eigenvalue lambda 2. Let's assume that they are different, okay? And I guess we are going to play a similar trick as we did before. So we will start with this equation, and we will dot it from the left with v1. I assume I don't have to explain that this indeed is a dot product, right? V1 transpose this. This is a vector. V1 transpose means a dot product between this vector and this vector. Okay? I think you should be quite comfortable with this now. So again, lambda 2 is just a scalar, and this time a real scalar, so it doesn't matter where I write it because everything is commutative here. And the second set of formulas that follows from this, where I do the funny thing that I dot it with v2. Okay, so basically imagine that I just put v2 transpose to both sides of this equation. Okay, and here I just bring it together too. Okay, what happens next? So the one thing, did I forget something? What happens next is that you realize, so what is this as a type? What is the type of this thing? It's a v1 transpose AV2. I guess I should like remind you that A is an n by n matrix, right? It must be automatically if I say symmetric, automatically means square, right? and v1 and v2 are eigenvectors of it, so automatically means that they are n-dimensional vectors, right? So the type of this is what? If you do your like syntax check, I guess, scalar or 1-by-1 matrix, right? That's the same thing. So the 1-by-1 matrix or scalar has the funny property that if you transpose it, you get the same thing. But that's trivially symmetric, right? If I should put it in like the symmetric language. So that means that you can write it in the other way, right? You can write it as v2 transpose AV1, okay? So that means that these two things are actually the same, right? Because this is the same as this. That's what this line shows. Okay, doesn't look like it at first, but if you're like, oh wait a second, this is 1-by-1, it's perfectly symmetric. I transpose it, and again, the key thing here is that A is symmetric. Okay, that AT, this transpose here normally I would have to write AT here, right? But because A is symmetric, the T goes away, and I'm just back to what I had here. That's the key thing. Well, and if these two guys are the same, well, then these two guys have to be the same, right? So that's what I write here. Lambda 2 v1 2 v2 equals lambda 1 v2 transpose v1, or the dot product of v2 and v1. And what this means, if I should put this together, so of course, this is of course equal to v1 transpose v2, right? So this is equivalent to, if I should put it together, I will put it together like this: lambda 2 minus lambda 1 v1 transpose v2 equals 0. Are you following me? That's good. And notice that I assumed here conveniently that lambda 1 is not equal to lambda 2, right? So what that means is this is a scalar which is not 0, because I assume they are different. What is the type of this? Well, that's a dot product of two vectors. That's also a scalar, right? But if this guy was not 0 and this has to give me 0, well, I have no other possibility than this thing must be 0, right? And that's a dot product of v1 and v2. If the dot product is 0, that means that the two vectors are orthogonal, and that's exactly what we wanted to prove. To make it a proof, I make like a little square here. Okay. Yeah, I don't like these proofs like super much because I don't think they really buy you any intuition. So it's like sort of to be like cool to like say I can prove it, and it's sort of cool. But in terms of like practical applications that like in your engineering practice that you will really need it, maybe not. So I'm not gonna go into like proving all the properties of this, or I guess the stronger version. I'll just tell you the complete result. I guess that could be called something like a spectral decomposition for symmetric matrices, or well, let's just call it like this: spectral for symmetric matrices. Spectral or eigen decomposition, that those terms are used interchangeably. So what it means, if I have a matrix A, which is a square and symmetric matrix, AT equals A, then always exists an orthonormal matrix Q, so ON, that means orthonormal, and lambda diagonal. How could I write this? Maybe like this, diac n, diagonal, such that A equals Q lambda Q transpose. Okay? So there are no special cases, no assumptions that the eigenvalues would have to actually be distinct, like in the general case. So we always have a full set of eigenvectors. Again, I'm not going to do the proof. If you are interested, you can find the proof, for example, in the Gilbert Strang's textbook. But I'm not doing it because it's like a little technical and not that useful, at least in my opinion. I guess the only trick here is to deal with the repeated eigenvalues. So you need to show that even the repeated eigenvalues, you can find orthogonal eigenvectors. And I guess you need to be a little bit careful because you could also easily find not orthogonal eigenvectors, but you can actually make them orthogonal. And if you do that, you get this eigendecomposition. So basically what this theorem is saying, if I should just rephrase it in English, is that eigendecomposition for symmetric matrices works perfectly and with an orthonormal matrix. Okay, so no need to go to complex numbers, and as an added bonus, I get an orthonormal matrix here. Which, oh, okay, no need to confuse you. Okay, so let's look at very important, I guess, application of symmetric matrices, or maybe it's even like a different view on symmetric matrices, if you will, and that's looking at quadratic forms. So what are quadratic forms? By definition, they are multivariate polynomials, multivariate degree 2 polynomials. You know what, let me just use this paper and give you some examples in small dimensions first to make it very clear. So this is the spectral decomposition theorem. So what do I mean by quadratic forms? So in 1D, quadratic forms will be very simple. There will be functions that look like this, where a is a real scalar. Okay, so that's a function from R to R. So not even linear and constant terms. That's what I meant by a degree 2 polynomial. So here it's not even multivariate. So that's easy. Gets more interesting in 2D. So in 2D, a quadratic form would be this, a general quadratic form. So notice that all these monomials here, they have the same degree. They all have degree 2. Okay, that's what a quadratic form is. And those are all the degree 2 monomials you can create from x and y. If I was gonna go to 3D, then I will get more of them, of course. So I will get ax squared plus by squared plus cz squared plus dxy plus exz plus fyz. And again, all these things, a, b, c, d, e, f, they are just real numbers, okay? Arbitrary real numbers. So that's what quadratic forms are. So how would we write the general formula in Rn? So here I would grab a vector x, which has components x1, x2 up to xn. Okay. And I would like to generalize this. How would you generalize this to R to n? I guess you sort of get the idea, right? I get all pairs, right? And each of the pairs gets a coefficient. The question is how to write it elegantly. That's actually the beauty of linear algebra. It lets you write all these things very elegantly. I guess you could write some messy expression using sums, and it would be a disaster.
What does the x vector mean?
Oh, that's just my variable. So here I was just calling it x, xy, xyz. I could have called it x1, x2, x1, x2, x3. In n dimensions, I will run out of letters, so I have to call it x1, x2, and xn. So it's always a function, right? So I guess I should have said this. This is a function from R2 to R, the function from R3 to R. So of course here we're gonna have a function from Rn to R, right? It's gonna be sum of a degree 2 monomials, okay? The question is, how do I elegantly write the analog of these formulas for n dimensions? So how do I write, what do I write here, right? If I'm to continue in this sequence. Any ideas? It's actually very simple using matrices.
Diagonal matrix.
That would not cut it, right? Well, let's take a look at how could I mean, I don't know if it makes sense to be spending. Probably not. No, it's not. It doesn't have to be a diagonal matrix. It will be immediately obvious. I just want to write this instead of doing sums. I want to write it using matrix vector multiplication. Well, okay. Let's think about it. Let's think. Maybe it's a good exercise in the formalism. So how would you do the R2 case? So if I had a vector here, so let me get a little bit easier. So if my vector xy, so I write this x and y as a vector, okay. And then I want to write some matrix here. And then I write the vector here. So I already told you the structure, right? So this is gonna be the vector as a row vector, the same vector as a column vector, okay. So obviously here I probably want to write A, right? Here I want to write B, right? Because this is gonna be the term that gets y squared, right? And what shall I write here? That's the slightly tricky thing.
Should be a C something. Half C.
Exactly half C, that's correct. C half, and here is also C half, right? That's because here I get the xy term essentially twice, right? Again, I'm relying on your mental picture of matrix vector multiplication. If you multiply this through, you will get exactly this, right? So now it's obvious that in the n-dimensional case, this is just xt a x, where A is an n by n matrix, okay? Real matrix. Now the cool thing is that without loss of generality, I can assume that this matrix is symmetric. So that's how we tie this back to symmetric matrices, or I guess that's why it belongs to this chapter at the first place, okay? Well, let me try to convince you about that. Let's take a look at the 2D case. And let's just put there a general matrix, okay? Let's see what happens. So if I have xy and I put there a general matrix, how shall I call the elements? Let's call them A11, A12, A21, and A22. Absolutely arbitrary matrix, okay? What do I get if I multiply it through? Well, I will get x squared A11, then I will get xy A12, then I will get yx A21, and finally, it's lame that it didn't fit there, but the final thing will be y squared A22, right? So this I can put, sorry about the spacing, so I can put this, we put this here. So I can put these terms to, so yx is the same as xy, right? So I can put it together and I can say that this is xy A12 plus A21 plus y squared A22, okay? So that's just matrix vector multiplication. I hope everybody sees that more or less immediately. Well, so what does this mean? That means that as long as the quadratic form, as long as this function, that's the quadratic form, so this is a general n by n quadratic form, as long as the quadratic form is concerned, it doesn't really care what is in A21 and what is in A12. It only cares about the sum of them, okay? Maybe I can give you a more concrete example. Let me give you a more concrete example with some actual numbers to make it to really nail this. So it doesn't matter if I have this quadratic form or this one, 1, 3, 3, 1. They are exactly the same, okay? Why is that? Well, because this, how would I do this? Like this. That's because the A21 and Y2, they get summed, right? So as long as the sum of the diagonal elements is the same, then they are exactly the same quadratic forms, right? So of course, I don't really have to, so that means why? Without loss of generality, I can assume that this matrix of the quadratic form, or this matrix A here, is symmetric, because if it was not symmetric, all I need to do is this. I can just say, this is going to be equal A plus A transpose half X, and this is definitely symmetric. Okay, why is that true? Well, that's again because, I don't know if I'm not spending too much time on something that's already obvious, but let's just finish that. This is equal to that, right? So I can put it there twice, divide by 2, and I get A plus A transpose divided by 2. So again, indeed, So let me write it here. VLOG, do you know the VLOG? Without loss of generality, A is symmetric. Which means if I restrict myself to symmetric matrices here, I'm actually not losing anything. So that's what we're gonna do, of course, or I mean that's what everybody does. If you are talking about quadratic forms, then it's automatically being assumed that the matrix here, that the A matrix, this matrix of the quadratic form, it's automatically assumed that it's symmetric, because it would be dumb not to be using their symmetric matrix because you get the same result, and things get easier for symmetric matrices as we have just seen, right? They have real eigenvalues, and these eigenvalues of quadratic forms, they let us characterize different types of quadratic forms. So you might have heard, maybe even from me, these terms before: positive definite, negative definite, semi-definite, and indefinite. So let's go through it. What does it mean? So those are types of quadratic forms, okay? And it works not just in 2D, it works in n dimensions exactly the same way. So we say that a quadratic form is positive definite if its matrix has all eigenvalues strictly greater than 0. We already know that they must be real because the matrix is symmetric, right? So we can talk about being greater or smaller than 0. And positive definite means all the eigenvalues are strictly greater than 0, okay? By the way, that means that the quadratic form, if you look at it as a function from Rn to R, that means that the function is convex. I don't think I ever defined convex function, right? So let me just say quickly what is a convex function. So we say that a function f, which could be an n-dimensional function, you probably know this at least for one-dimensional function, I guess. But for n-dimensional, it's similar. So the f is convex if and only if, I guess that's one of the definitions, there are others too. So if I pick any two points from the domain, then it must be true that if I take the function on a linear combination of x and y, then I must get something at most the linear combination of the function values of x and y. Oops. Fy here, okay? So the picture is like this. If I draw a 1D picture, that's easiest to draw. So if my function is this, means if I pick any x and any y here, that's my x, that's my y, then I get the fx here, right? And I get an fy here. And this says that if I'm doing, what does it say? If I'm doing linear interpolation between fx and fy, that's what y minus t. So the t is a parameter going from 0 to 1. So that traces this line. That's the right-hand side, right? And this says that the function, if I interpolate in the parameter domain, then the function has to be below it. Okay, so if for like t.5 would be, I would be here. That would be on the right-hand side. And the function at t point, this left-hand side for t.5 would be here, and this looks like it's convex, right? Because this right-hand side is indeed above that. Okay, so that's convex.
So it has to always curve upwards.
Right, exactly. And in 2D and 3D and so on, it's the same idea, right? In 2D, you would have like a bowl type of thing. In 3D, it's a little bit harder to imagine, but it's the same idea generalized to more and more dimensions. I guess I have like a so it's a lame picture, but I have a picture like this here. Yeah, I don't know if I would call it a volley. I'd probably say like a bowl. Okay, so positive definite, it means the function is convex. Convex functions are very important, for example, in optimization. Actually, I think we will get there. You know that optimizing a convex function is easy because its local minima are all automatically global minima. So that's why there is an entire discipline called convex optimization, which essentially means that convex optimization problems you can solve efficiently. But I guess I'm sidetracking. So I need to go through the other one. So negative definite means that all eigenvalues are strictly negative. Okay. So that's basically the same idea of positive definite turned upside down. Okay. So that actually means the function is concave. What is concave? F is concave if minus f is convex. Okay. So it's exactly the same idea turned upside down, basically like this. Okay. So instead of a bowl, you will have like a little peak, typically not sharp. That could also be sharp. Doesn't matter if you don't care about a continuity. Positive. So these semi-definite versions, they basically mean that we relax this sharp inequality into a non-sharp. Okay. So positive semi-definite means is defined as all eigenvalues have to be greater or equal than 0. Okay. So that's similar to what we can say about convex functions. We can talk about a strictly convex function. If instead of this I will have this, then I talk about strictly convex function. Can you tell the difference between convex, or tell me what is the difference between convex and strictly convex? What would be convex but not strictly convex, for example?
There's a straight part.
Exactly. If there is a flat straight part, then this will hold with the equality, right? But it will not hold with a strict inequality, right? Or I guess in more generally, I could have something like this. I could have something that's convex, then it's straight, and then it's again convex, right? So this would be convex but not strictly convex, because in this region the strict inequality would not hold. Okay. So what does it mean for the quadratic forms? Well, here I would say it can be more like a valley actually, because the difference is that some eigenvalues here might be 0. Okay. So instead of a bowl, you can still have a bowl, but in one direction it can be perfectly flat. So imagine something like a Grand Canyon where the river would be like just a line. Okay, something like this. I wish I prepared a picture, but I didn't. Some sort of like U-shaped things translated along the line. That would be allowed for positive semi-definite. It would not be allowed for positive definite, where it would have to curve up. Did I convey that idea? Imagine something like a Grand Canyon with a straight linear river inside. That being the minimum. Or the other way you can look at it, that if we look for a minimum of a positive definite function, it has to be unique. Okay. It always looks like a bowl, so there is a unique point at the minimum. Okay. If it's positive semi-definite, it won't be unique. There can be an entire line of points where the minimum is, or entire subspace in general. I can have multiple eigenvalues which are 0. Okay? Negative semi-definite, same idea. Here I want less than or equal than 0, so it's a relaxation of the negative definite. Yeah. And the final case is indefinite matrices or indefinite quadratic forms, which means that there is both a positive and a negative eigenvalue, meaning strictly, of course, otherwise it wouldn't make sense. Okay. So either it doesn't. So from the complexity standpoint, or from how complicated of a function, it doesn't matter at all if it's convex or concave, because concave you can just flip it. You can just take minus f, and you will get back to the convex case, right? But the indefinite, that's something different, right? Indefinite can be something like this in 1D, right? Or something that's neither convex nor concave. You would probably just say non-convex, right? And that means that's something more complicated, something that does not have local optima being equal to global optima. So let's take a look at 2D quadratic forms on this figure. It's not the most beautiful figure, but I think it will get the idea across. And yeah, symmetric matrices and quadratic forms, they are basically like brothers, because the quadratic form and the symmetric matrix is essentially the same thing, right? The only difference is that in a quadratic form, you just plug their xt and x on the left and on the right. So It's essentially the same idea. So we're in 2D. Here are at least the 3 cases visualized. So this is the positive definite. So it looks like a rotated bowl type of thing. Negative definite is the same thing flipped upside down. And here is how an indefinite thing looks like. That's interesting. So how would you characterize it? I would say it's like a saddle point. So what happens here in one direction, like I guess if this was the x-axis and if this was the y-axis here, so this was the y-axis, the x-axis. So the x-axis, it is convex, and if I slice it with a plane, in one direction I will get it convex, and in the orthogonal direction I would get concave. Okay, so that's what indefinite means, that there are some eigenvectors that have positive eigenvalue and some eigenvectors that have negative one. Okay, so that at this funny point, at this saddle point, that's exactly where they meet. So you can so the saddle point is actually like this special case of a point that's a critical point. At all the derivatives there would be 0, but it's not a local extremum. Okay. I guess we will clarify that when we will talk about optimization. Oh, you might be asking how the semi-definite would look like. Semi-definite, I think I sort of explained that, right? It would be sort of like a degenerate type of ball which can be completely flat in one direction. All right, so one way we can study, or another way how we can look at quadratic forms is to plot their level curves, okay? So I will look for a set of points x such that the quadratic form is equal some c, where c is a constant, okay? So I guess more formally I could say I'm looking for all x's such that xdax equals c for a given c, okay? That's basically what I draw here, these things. Or you can imagine that you are doing this. Imagine you have this plot, okay? So it's a plot of a function, in this case from R2 to R, and you slice this with a plane, okay? Like imagine this was going out of the plane, and you just take a plane. I guess you can't really see that. If you take a plane at some height and just slice that, okay? And the curve you get, that's the level curve. And it's interesting to think about what they are for the different types of quadratic forms, because they are called conic sections. And for positive or negative definite matrices, you would get ellipses, okay? And for indefinite matrices, you would get hyperbolas. So ellipses would be nice closed curves, but hyperbolas would be not. Again, look at this picture. Imagine slicing this. So if this is the z-axis in all 3 cases, imagine slicing it with a plane which is perpendicular to the z-axis at a given height. So what you get here, I guess that's what visualized here, you would get hyperbolas like this. Oh, what do you think, that's not written here, what do you think you get for the semi-definite matrices? It's like a degenerate case of an ellipse, if you want to think about it that way. There is another bola, which you get for semi-definite matrices. You get a parabola. It's sort of like a corner case of the ellipse. Okay, and now let's see how does it tie back to the linear algebra and eigenvalues and eigenvectors. And it turns out, so let's look at the positive or negative definite matrices. We can just talk about positive definite, right? And negative definite just means flipping the sign, so there's nothing special happening. And the principal axes of these ellipses, they are the eigenvectors of the matrix, of the symmetric matrix A defining the quadratic form. From what we said before, the eigenvectors of a symmetric matrix, they are mutually orthogonal. So that's nice. So that means the principal axis of the ellipse will be mutually orthogonal. That's nice. And the dimensions of the ellipse will be related to the eigenvalues of the matrix. Okay. So let me explain that a little bit in a little bit more detail. So let's try to understand the behavior of a quadratic form by looking at the eigenvectors and eigenvalues of the A matrix. Okay. So I used the spectral decomposition theorem, which I said some time ago. So that means that A is equal to Q, let me write it here, Q lambda Q transpose, okay, and let me plug it in here. So what I can do here, instead of xtq, I can write qtx, the whole thing transposed, okay, and I did this so that I have here and here the same term, okay. What was Q? Remember we said that Q will be is always an orthonormal matrix, okay. I can say even more, actually. I can always make it a rotation, actually. You know that orthonormal matrices may or may not be rotations, right? But in this case, I can always make sure that Q lambda Q transpose, that if I have this, I can make sure that Q will be a rotation. If it's not a rotation, so first of all, how do you tell if Q is not a rotation? Now you already know that. Yes, the determinant is actually -1, right? If it's orthonormal matrix, determinant can be either plus or -1. If it's a reflection, if it's not a rotation, the determinant will be -1. So we can fix it quite easily. If you just look at what does this matrix product mean, it will immediately be obvious how to fix that. So this is just this type of product, right? I'm just writing it out to make it clear. So this is Q1 transpose up to Qn transpose. So this is just a sum of outer products. So lambda I, Qi transpose, right? If you do the matrix multiplication in this way, you see that this is exactly that. So if the determinant of this was -1, of course the determinant of this is -1 too, right? Because we know that the transpose of a matrix does not change the determinant. Well, that's easy to fix, right? All I need to do is to take Qn, I don't know, hat, which will be minus Qn. Or I could flip the sign of any column here. Okay? Here the flip signs cancel. But in the determinant, it means it will flip the sign of the determinant, because I multiply one column of a determinant by -1. I flip the sign, I will get determinant 1, so I will get a rotation. So that's an easy fix to that, okay? So yes, so I can furthermore assume that Q is a rotation. And what does this mean? Well, that means that the QTX, that's some different vector, y1 and y2, and I can look at it as a change of coordinates, as a change of coordinates from x to y, okay? Or I can say that the y1 and y2 are coordinates of x with respect to basis q, okay? Remember how we talked about a change of coordinates? I guess was also your first midterm problem. So if Q is a rotation, it's a particularly easy change of coordinates. And if I perform this change of coordinates, so if I change from coordinates x to coordinates y, it turns out that actually somebody was suggesting this, that the matrix could be just diagonal. That happens to be the case if we pick the basis of our coordinates to be the matrix of the eigenvectors. Because look at this. So if y are my new coordinates, qtx, then the matrix of the quadratic form reduced to just a diagonal matrix. Okay? Because here I have just, and I can write it out as lambda 1 y1 squared plus lambda 2 y2 squared. Okay? Because this was the matrix of eigenvalues. Again, all are real here. Everything is cool. Here are zeros if you want me to fill it in explicitly. Yeah, so if you want to look at this graphically, so if I look at a general quadratic form, I don't know what this 30 here is. Sorry, I didn't mean that. This is the origin anyway, this point here. So this is some quadratic form, and if this was my original x1 vector and x2 vector, then in the original coordinate frame, the quadratic form was like a rotated ellipse. But once I find the eigenvectors of the quadratic form, the eigenvectors will be this, y1 and y2. Then in this rotated coordinate system, it's an axis-aligned ellipse. Okay, an axis-aligned ellipse that basically corresponds to a diagonal matrix of the quadratic form. Okay, so you can see this is like a canonical ellipse. Or if I guess if I would put there some right-hand side, right? So I guess let's go through that slower. I guess I'm trying to rush it. Okay, we are talking about the case when of a positive definite quadratic form, so both lambda 1 and lambda 2 are positive. And the ellipse is the level set, so I say that this must be equal to some value. Well, let's just pick 1, for example. That's an easy one. And it turns out that the eigenvectors are the principal axis of the ellipse, and the lambda 2 and lambda 2, they are related to the extents of the ellipse. How are they exactly related to it? Well, that's quite easy to see, right? So what is the... Oh, let me draw another one here. So if I already put it to the y system here, so this is my y1 and y2. So what is this length here? Well, and this is the level set corresponding to 1. Well, what this means, if I set y2 to 0, right, then I will get lambda 1 y1 squared equals 1. So that's easy to compute that. From this follows that y1 equals 1 over square root of lambda 1. Okay, so this will be 1 over the square root of lambda 1. And by the same argument, this length here, that would be the 1 over the square root of lambda 2. Okay, and the matrix Q, the matrix of eigenvectors, it can be interpreted as a change of basis. So the matrix Q converts from the y basis, converts coordinates from the y system to the x system. Conversely, the Q transpose would be performing the change of coordinates from the x basis to the y basis. And why do we do this? We do that so we simplify the matrix of the quadratic form to a diagonal matrix. Okay, so let's cover this too. So this is essentially what I did before. I said that in this specific coordinate system, the quadratic form reduces to a diagonal quadratic form. And here we have an equivalent. From this we can realize a different equivalent characterization of positive definite matrices. From this we can see that if A is positive definite, that's if and only if xDAX is always positive for every non-zero x, okay? And similar thing would work for the negative definite, okay? So let's look at, and I'm saying this is equivalent definition. It's actually in some books they define it this way. They just say that a matrix is positive. A symmetric matrix defines a positive definite quadratic form if and only if xDAX is always positive for all non-zero x. Of course, for 0x you get 0 here, so that's trivial. Okay, so this if means that there are like two implications, right? So one of them is obvious, right? Because if A is positive definite, then using our definition, we said that means that all the eigenvalues have to be strictly positive, right? But because if I assume that x is non-zero, that means that at least one of the y's must be non-zero too, right? Because why? Because y is q the x, right? And the norm of y is exactly the norm of q transpose x. which is just the norm of x, right? And if the norm of x was greater than 0, if x was non-zero, that's certainly the norm of y also must be non-zero. So there must be at least one non-zero y, and because all of these are positive, because it's a positive definite form, that this needs to be strictly greater than 0, okay? So if I, in other words, if I assume that A is positive definite using our definition, I can prove that xdAx is always positive as long as x is non-zero. So that's proving this implication, okay? To prove the other implication, that's also simple. So we need to go the other way around. So I need to show you that if I have a matrix A such that for every non-zero x, xdAx is strictly positive, I need to show that from this, all lambdas are positive. All eigenvalues are strictly positive, okay? And that's easy. All I need to do is to pick for x the eigenvectors, okay? So let's say that qi is eigenvector of A corresponding to the eigenvalue lambda. And I would like to prove that the lambda must be strictly positive to be equivalent to our definition. We defined it that all the lambdas are strictly positive, okay? Well, okay, from here, so eigenvector is a non-zero, right? No questions about that. So this applies, right? So that means that qi transpose aqi must be strictly greater than 0, right? But because qi is an eigenvector, this is qi transpose lambda I qi, right? The lambda I can come here. Here I have qi transpose qi. Well, this is definitely greater than 0, right? And from that follows that certainly lambda must be also greater than 0. So indeed, these two definitions are equivalent. Similarly, you could also show that it would be positive semi-definite. What do you think would be the difference here? Greater or equal. And then I can drop this requirement, right? Because for x0, that's also 0, right? And similarly, I could say negative definite. Of course, that's just flipping that. And I could say that it's indefinite if there exists an x such that this is positive, and exists some different y, non-zero, such that this is negative. I don't even have to say non-zero, because for 0 it'll be trivial is 0. So it'll be okay, so I think we will leave it here, and we will continue on Monday and not do anything on Wednesday except for your homework. Okay?